Okay, welcome to the next latest ZAG seminar. We're pleased to have Matt Ballard from University of South Carolina, and his title is Stratified Mackay Flops Revisited.
Thank you, Chuck, and thanks to all the organizers for giving me the opportunity to talk. It's a pleasure to be part of this excellent endeavor. So let's share my screen. Okay. Let's get everything set up. So probably should have done this before. Oops. Okay. So if I go, okay, well, never mind. All right. So as I mentioned before we started talking, it's Bondle's 60th birthday conference. So maybe I should have talked about Bondle's conjecture, and this could have been a satellite event of that. But if you want to see a talk on the proof of that, you can go see Alex Duncan's talk from Burrs recently. So what I'm going to talk about is perhaps one of the main motivating questions when we talk about the structure of derived categories and how it relates to birational geometry. Right. And so basic question is as follows. Right. So let's say I'm given some diagram, and we're going to declare this this needs to be a flop, and let's say smooth varieties. All right. So what you want to find is you want to find a single object on the derived category of the product such that if you look at the usual push-pull transform, right? So I take something, I pull it back, I tensor with P, and then I push it down. We want this to be an equivalence. And the language I'll use for such a thing is going to be, call such a thing a kernel. Yeah, usually it's called a Fourier Mackay kernel. It's an equivalence, but just a general. When I talk about an object on the product, I'm going to usually say the word kernel for it. So I did this in my linear algebra class when I talked about null spaces, and then I started lurching into the language of kernels, and I'm like, what is this thing? So I learned my lesson about at least telling people what kernels are before I go too far. Okay. So what is known about finding an explicit object that gives you an equivalence for certain things? So this question is very closely related to the Bondel-Norloff conjecture, which asks whether or not the two are equivalent over Y. Certainly, if you can find a particular object that gives you an equivalence, then you know that they are equivalent, right? And then a result of Orloff tells you you have an object if you have an equivalence, but it's not constructive. It's more of a specification. You know that there exists some object, in fact, a unique one, that gives you the equivalence. But how can we describe it in terms of geometry? What sort of structure might it have gets lost in that question. So what's known? So again, I said this type of question goes back to the original paper of Bondel and Orloff in 1995, right? And sort of if you think about it first and you try and think in terms of what's the least moving parts to make something on the product, well, maybe you could take the structure sheaf, or you could take something else. But the fiber product oops, its structure sheaf is pretty much what you're going to run into if you think about not needing to specify anything else and trying to pull out some object that will behave well enough to give you an equivalence between the two categories, right? And sure enough, this works in the example where it's called, sometimes called a standard flop or an ATIA flop. And we move up a bit, and a well-known result of Bridgeland says the same is true for threefold flops. Now, it's not exactly how he stated it if you look at the paper, of course, but it is a consequence. The consequence of what he proved is that if you take the structure sheaf of the flop, you get a 4-Mukai kernel, giving you the equivalence. Okay, so now you're feeling pretty good, you know. Low dimensions are good. Some class of examples are good, right? And then another class of examples that was verified due to Namakawa, what are called Mukai flops. Those also work fine. Okay, so we have, you know, a building body of evidence that we can maybe have a hope that in general, right, we can hope, one can always hope, is that this works in general. It gives you an equivalence for any choice of flop. And shortly after Namakawa's first paper, he had a second paper in this line. And so and what it says for stratified Mukai flops, and I'll tell you a little bit more about each of these types of flops in a bit. It doesn't work. The structure sheaf of the fiber product doesn't work. Surprisingly, even though you get equivalence on K here, the growth P group, at least K0, maybe even all Ks, I don't know. Right, and so sort of there ends the story for a holistic construction of an equivalence in general for flops, right? And constructing a 4-Mukai kernel. And what is a necessary hope if we're ever going to prove this? Although, you know, maybe you can wiggle around this, but really, if you're ever going to prove the original Bondel-Orloff conjecture, which says there is an equivalence, we're going to need a quote unquote natural construction of some P, right? You're handed the flop, hand me back something, purely depending on that. That gives me a kernel and should behave well homologically. Fiber product works in some nice cases, doesn't work in general. All right, so what else can we make with sort of no other information specified in here? Okay. And one nice result to get a handle on the structure of a flip or a flop is an observation due to Reed that was really fleshed out in Thaddeus's well-known paper on variation of GIT. And that's the following. So say I'm given, and I'm going to say smooth, but you don't need smooth. You have some, you can weaken this significantly, but let's just, for this talk, let's just say simplicity. So assuming this is a flip now, smooth varieties. Should turn my phone off. Then we can rephrase everything as the output of a GIT problem. Okay. Right, so meaning there exists a graded sheaf of algebras over Y such that if I take the product construction of the positive piece, I get X plus the relative product construction over Y. Take the relative product construction of the negative piece over Y, I get X minus. And then if I take the invariant piece, it's just the structure sheaf itself. Okay. So really, when you are thinking about the question of flips, your first thought should be to think about stability and invariant theory, because you can always reduce the problem to studying those questions. And the examples I gave before, at least some of them, have really simple presentations in terms of the rings that are involved, right? So usually here, right, I'm going to take Y to be affine because you can do this locally on the base. So, right, in our examples, this standard Atia flop is just specified by taking polynomials and two invariables, assigning weight 1 to the first n and weight -1 to the next n. Right. And then if you take, right, X plus is going to be, right, this is K adjoint X. X mod mod plus, X minus is going to be X mod mod minus, and then X0 is going to be Y. Y is going to be X0. So it's about one of the most simple invariant, invariant theory examples you can really dream up. And standard flips, you just let the two numbers of variables be non-equal. Okay. And then for this Mukai flop, right? So you do the same thing, except now you're not polynomial, but you're a quadratic hypersurface inside. Very simple, right? Okay. So this is the graded ring, and again, we've attached weights. Okay. And then for the stratified Mukai, it's a generalization of the previous one where we have, instead of a sort of one-dimensional space, we have an n-dimensional space, right? So I have maps. These are K vector spaces, right? And I assume the dimension of V is less than the dimension of W. All right. So I take K, A, B, and then I mod out by, let's see here, B, A. Okay. So that's just the previous example, but with a higher dimensional source and target for V. Okay. And then what's the action here? Well, the action is via the only the obvious GOV action you can put on this space here. Okay. So precisely, right. G dot A is G inverse, and G dot B is GB. So, right. So at least in the situations that popped up, both providing us examples of 40 Mackay kernels and ones that didn't, you have some fairly simple, representation theoretic questions and settings to think about, right? So, so what I'm going to be interested in, like I said, is can we figure out a way to construct interesting, right? So the goal of today, or the meta goal, is figuring out how to construct homologically well-behaved kernels in, right? So I have, I have G acting by X in, rings of functions on X cross X. Again, for simplicity, I'm talking about affine stuff, but the question is very easy to reduce to that. Okay, and I should note that there has been a lot of deep and interesting work that goes into the question of figuring out equivalences in general, right? When are two GIT quotients equivalent, as I vary the choice of stability parameter. But I will not comment on that because, like I said, I'm focused on making a particular object in a very hands-on and geometrically constructive way. Okay, but if you think back to Orloff's result, once you have an equivalence, you know that there is a kernel, and some of the techniques that exist will tell you things about the kernel. But let's see what we can make here before we say anything more, right? Okay. So so here's a construction. Okay, and this construction is due to myself, Helen Deemer, and David Favero from 2016. Okay, so right, so we're going to take G acting on X, and we're going to assume, like I said, X is affine, so I can talk about algebra as opposed to complicating it with things that are not necessary. Okay, and then let's also take a linear algebraic monoid M with the unit group being G. Okay, so we all have thought about linear algebraic groups. Okay, sure, we feel fairly comfortable about such a thing. Linear algebraic monoids, well, you just, instead of say group, you say monoid, right? And so if you want to think about examples, the two ones that will most, certainly not the only two, but the two ones that will most come into play here today are going to be G is GM and M is A1 with multiplication. Okay. And some higher dimensional version of this when G is GL. And M is just all n by n matrices. Okay. So those are two examples you should keep in mind when we think about what we're doing today. All right, so if I have this data to start out with, right? G acting on X, some monoid, and I know the units are G, or at least I know G is a subset of the units. I can deal with that too. What can we do here? Well, we get an obvious map. Right, I have two copies of functions on X. I have functions on M, and we can send that to functions on X cross G. Right, and so first we just send a function on X to itself. Next, we send a function on X to, well, whatever G does to it. Okay. And then finally, I have a, this tells me, up here it tells me that, G is a subset of M. So I can just, include the functions on M into the functions on G. Okay. And let's define Q depends on X and it depends on M, and I guess X with the G structure, so maybe I should put a G in there. But this will just be call this map, I don't know, phi, just to give it a name. So this will be the image of phi under this action, under this homomorphism, right? Okay. And so because I have two copies of X, right, I have naturally a bimodule over X, and this whole picture carries a G by G action, right, where I have sort of G1 on X. Let's see, let's write it here. So G1, G2 on X is just G1 X. Let's see, is this right? Might be basically the only thing I can do. Yeah. And then G1 M, oops, G1 G2. So we get a G by G equivariant KX bimodule. Okay. And this bimodule includes into functions on X cross G. So I'm going to call that delta. And then we have some quotient, which I'll call S. Okay. So why do I call this delta? Well, if I think about, right, if I think about phi delta from the derived category of G equivariant things on X to the derived category of G equivariant things on X, then this is isomorphic to the identity functor. Okay, so it's some cover of the identity functor for the chart given by X, smooth chart given by X and X mod G. Okay. Right. Okay. And so if we want to do a simple example, we'll do some more examples here in a bit. Right. So I could take, the ring that we had before. It's the standard Atia flop, right? So this has weights 1, this has weights -1, right? And U dot xi is just U xi, and U dot yi is U inverse yi, because those are the weights. And so Q is going to be generated by, well, you have the x's, right? And then you also have U. So you don't need these copies here for this second part of the action, because you can generate them with U and X1. But this is something you can't get from the y's, right? I can get the y's from U inverse yi by multiplying by U. So it's going to be the subalgebra of kx1 through xn, u inverse. So, oops, I should have wrote that as u inverse I, generated by these particular, oops, yeah, we need the y's too. They don't go away. So it's going to be the subalgebra generated by these particular elements. Okay. Right, and if I take again we have maybe here I provide different vector spaces, but we have some linear maps, generic linear maps from V to W1 and W2 to V, and right, and then you let A carry this action, and you let B carry this action. And I think about what Q is. Well, I'm going to need B, right? I have G. I'm not allowed to use G inverse. I have B, and then I'm going to need a G inverse. It's contained in K A B. G really, I'll put invert the determinant here, so we just keep in mind that's what we're talking about. Okay. So what's known about such things, right? So taking subalgebras generated by stuff is a common thing to do in commutative algebra. Can we say anything useful homologically about this? So going back to the paper with the original construction, BFD, right? So with this, scroll back up here for a second. So with this natural transformation here, what we can do is we can think about, right, if I right, I can take Q, I can tensor it over itself. Now really the direction in which I tensor it is important because the two actions are not the same. So I can do this, I can tensor it over R, right, my base ring, and then I can take invariance, sort of the invariance in here and in here. Okay, so this operation here, I'll write as Q star Q, and it is the operation on the kernels that descends to composition of functors when I pull back, tensor, and then when I push down, I take invariance with respect to the factor I've pulled back on. So I still have a single G action in the end. Okay. So oops. So with this natural transformation, like I said delta star whatever is naturally isomorphic to whatever. And this is the identity, right? So I get a natural map from Q star Q to delta star Q and in the other direction. And the result, right, maybe I should have. So let's notice a few things. We can do these constructions. And so now let's look at the case where G is just single GM. M is A1. Okay. So then, well, from this paper, what can we show? Well, in general, what I'd really like it if this was an isomorphism, right? That's an isomorphism, then I have some type of canonical idempotent inside the derived category of bimodules, equivariant bimodules over my original ring. And that's what you have, except you have to be a little bit more careful. You need to derive the question to get the right answer. So what you have is you have the derived construction gives you a bimodule, an idempotent bimodule inside here. Okay, so really, what have I done? I've taken R and then I've put it in some model category and I've replaced it. This is some cofibrate replacement. And Q dir R is just a Q of this cofibrate replacement. Okay. Right. So every graded ring, and this is true for every graded ring, right? So every graded ring.
Matt,
Yeah.
at least for me, the screen is not updating. So I only see Q star Q goes to delta star Q. I don't know if it's the same for everyone.
Oh, okay. Is that the case for other people too?
Yeah, same here.
Okay. All right. Let me try and toss this up into a Zoom link so that you can look at it in your browser. And that way you can scroll separately too. So let's see. Here's my notes for the talk. You can see that. Try and join here. Turn without video. Got it. No audio. All right, so let's see. Clicking, chat. Oh, no, that's not a link I wanted. Copy, share link. Where was I here? Okay.
Yeah, we can see more now.
Oh, it refreshed. Let me copy this. I still would like to give this to you because, so if you go to that link in your browser, you don't have to follow the Zoom window anymore. You can just go to your browser and you can scroll up and down all you want. You can even write on this if you want. Enough trust there. But I find it much easier to peruse a written talk if you can scroll yourself and go back and look at the information. Okay. So can I get any kind of confirmation that the link worked?
Yeah, the
Yep,
link
you did.
worked, but also it looks like it might have refreshed. You want to try writing on this one?
Okay. How's that?
Yeah, it's good.
Okay.
I think it just froze for a bit.
Oh, okay. So hopefully, hopefully that is not going to continue. All right. Thank you for letting me know, though. But it's a good point to break for questions, right? So are there any questions so far? I also have to reorient where I'm in my notes. Another good reason to break for questions. Okay. I'll take that as no questions and continue. Okay, so what we have here then is we have this canonical idempotent built just from the action of GM on this ring, the grading of this ring alone, because really, there's not a lot of monoids I can build when I just have GM, right? I can basically put in the origin or I can put in infinity and they both look the same up to inversion. Okay, but the real nice consequence of this type of identity is that what you immediately implies that you get a semi-orthogonal decomposition of the derived category, the G-equivariant derived category, in terms of the image of these two pieces. Remember this S-dir here, you can scroll back up and you can see it's just the co-kernel, the map to the identity, right? And moreover, you can actually get a three-term semi-orthogonal decomposition. One looks like the piece before. Another is some category we'll call W. And then the third is this intersection with, gee, I put the G on the bottom. Maybe I'll put the G on the top, right? That way I can put, this is the unstable locus. So we get this three-term semi-orthogonal decomposition, and then what you know is that if I take W and I restrict it to semi-stable plus, and then I pass to G invariance, then this is actually equivalent to the derived category of X plus, right? So the word for such things these days is windows. Okay. So a choice of a monoid will give you such a window in the derived category, at least for this GM case for a general ring. Okay. So in our examples, if I take right. Let's take the simplest example right here, just the standard flop. I take Q of this thing. Well, it's actually isomorphic to just adjoining U. Okay. And if I take, oops, I missed the Y's. Maybe we can do M's, we can do M's, right? This is not an isomorphism of bimodules because, well, I have to specify some action here. It's not just the usual action of diagonal tensor U. And if I take it and I restrict it, I restrict this to the semi-stable plus or the semi-stable minus, it's going to be isomorphic to this fiber product, the structure sheet for this fiber product. Okay. So the thing that gets spit out here in this very simple example of a standard flop is the thing that will give us the equivalence here. Okay. And then if I do it for this Q dir here for I get out something that looks like the total space I had before, but now I have a U included in my relation. So there's an extra component, much like you have when you talk about the fiber product. And again, this is if I restrict it to semi-stable plus, or minus plus, but at the same time, this is, oh, I guess, sorry, this should be minus because I have minus there. My apologies. It's still the fiber product, okay? All right, and then, well, you can try and compute this in general, right? But what you need to do is you need to compute a cofiber replacement, at least in the category of commutative K-algebras. Okay, so that's easy for complete intersections. That is not easy if you're not a complete intersection in general. So, right. So complete intersections, we're happy. Not a complete intersection, we're thinking. But I should say, work of Nitten and Favero, right? So if, right, if you have some conditions, say all the homological generators of our twiddle are in homological degree or in graded degree 0, then you actually get an equivalence. Then QDIR gives an equivalence in this GM setting. Okay. So the stratified, sorry, the regular Mukai flop is an example of this. But in general, you won't necessarily have all your homological degrees and homological generators in degrees. Okay. And so that's what's known in the case of just a single GM action. You can also, right, if you think about the general definition, you can also think about what is going on when I have more groups, right? When my group is bigger, different from GM, right? Certainly, if I have a torus, there are many, many affine toric varieties with that as the big torus, right? And we have some way to control that. Here, let's because of the focus here, let's take G equals GL, right? And let's take the right. Let's take this graded ring we had from before, right? Right. So the flip here is what's called a Grassmann flip. Okay. This is called a Grassmann flip for the diagram we get. Okay. And so let's say this is 20, myself, Nitin, David, Patrick McFadden, and Rob Vandermoor. In 21. Okay, so if you just take, we show that Q star Q underived is just Q. 4, we have to take the monoid, right? And the monoid is just going to be matrices. Okay. So Q star Q is Q. And as a consequence, we get the same results that we had back up here. Right, where'd it go? Right, we get a semi-orthogonal decomposition like this, and we get this window. Right, and then the window we get is just generated by.
So Matt, just so you know, for a while it's been frozen again, but I'm just reminding people that they can go to the Scratch page, the Scratchboard page.
Is that still working?
Well, it's working, although I'm on my phone, I can't scroll down. I just want to confirm that people are
Yeah,
able to follow.
it's
Oh,
working.
and now it updated.
Okay.
Okay.
Maybe I'll keep the.
All right.
Yeah, I generally follow the web page. I think is usually a bit better.
Sure. Okay. Sorry to interrupt.
But I'll keep the web page open and hopefully notice problems beforehand. Somehow I've lost the Zoom screen behind all my cascade of windows on my machine that are open. So these are representations described by Kapranov. They're not really representations of Kapranov, but they're the ones that provide a full, strong, exceptional collection of vector bundles on the Grassmann. All right, so you have some Young diagrams that have to fit in the prescribed box, K by N size. So in the sense, you know, you can say, you know, why are these objects? Why should we look at these objects? Well, it's because, you know, if I want to try and extend the action to matrices, that's naturally what's going to come up in terms of trying to resolve the corresponding object. Okay. All right, so And then moreover, right, so I said we had two different dimensions, right? We had a going to W1 and B going to W2 to B. Right. If the dimension of W2 is bigger than the dimension of W1, then you get a semi-orthogonal decomposition of the derived category of one of the GIT quotients in terms of the other for the smaller one. And we have an explicit description of the component, of generators for the components. Okay, so the fact that you had, I think, a fully faithful functor was known to Luschke, Buchwitz, and Vandenberg. Of course, they didn't know what this thing was, so they didn't know that it was induced by this particular idempotent up top. And then the description of the semi-orthogonal components is new. Okay. All right, so that's what's known. And today, in the last few minutes, unfortunately, what time is it? Why does that's strange. The time on my tablet.
10:50.
Yeah,
if
if you can see my screen, it says 9:41 on my iPad.
Ah.
So I think the iPad is the issue with something not updating. Okay, yeah, 10:50 makes sense. I have independent confirmation from my watch and from the laptop. Okay, so what's a simple representation we can make for GL, right? Well, it's the adjoint representation. So I'll take T goes from V to V, and then I'll have G act on it like this. Okay, and the question is, so I'll put it vaguely, and then we'll get a more precise one here in a second. So what is this thing? So if I take, T, I take a GT, G inverse T, and I take G contained in KT, G det G, right? This thing here, can I understand it? Does it satisfy this condition that Q star Q equals Q? And from that, can I deduce certain properties? Okay. And so here's a proposition. All right. So if I have a resolution, say over X1, X2, and this is in general, G, of Q, right? I have a free resolution. And the weights of each of the pieces are contained in a product of cones, right? So this is a G by G action. So on one side, I have an action of G, on the other side, I have an action of G, and I can talk about their dominant weights or just their weights in general if I want to talk about a cone. So here, sigma is so the cone of weights of Km. If I think about a monoid, I can extract out a cone of weights, which are just the functions with that weight inside Kg functions on G. And you can understand which monoids you have up to these cones. This is fairly well understood territory at this point. But what I want is I want to know that the weights of my components in my resolution actually live in the product of these two cones. So if I know that, then this will imply that Q star Q is isomorphic. So indeed, I have some idempotent in the category for these things. Okay. So let's see. So we want to use that now, right? So this is a general result. so here's the question. So what are the weights of a free resolution of right? In particular, do they live in this particular cone, the product of these two cones? Okay. And so for say dimension of d equals 2 and 3, the answer is yes, they do. Okay. And up to maybe if I gave this talk in a month, we would have it in general, or maybe not, but the general case doesn't seem far off. Okay, I'm being recorded, so I have to be circumspect here. Okay. So this implies Q star Q is Q, right? And moreover, right? So instead, maybe I look at K, A, B, and T. So A is before, right? B is before, and T is here. Okay. So this implies that if I do Q of K, A, B, T, then this also satisfies. Just redefine this to be Q. So this also satisfies Q star Q equals Q. Okay, it's not so hard to deal with Q star Q when the action kind of extends to the monoid on one side or some other side. Here, extending the action of the adjoint action to matrices, problematic, right? But for these other two, at least up to inversion, I can understand how to extend these. Okay. So, okay, and then so theorem. Again, we're going to restrict to n equals 2, 3, but I'm not going to be explicit about it now. Okay, maybe I say 1, 1, and 2, right? So if dimension of W1 is less than dimension of W2, and I pass to the GIT quotients, then I have a semi-orthogonal decomposition like such, right? And I can toss in a superpotential. So let's toss in the superpotential where I take the trace of so I have I have this as a module, let's say left, right, and then a copy of M. So let's say we'll do left AL BL minus R BR AR. And so if and I have to be careful now, so the dimension. So this is the case W1 is isomorphic W2. So we get equivalence of graded matrix factorizations, GL graded matrix factorizations on X plus of W and X minus of W. Okay. But if you think back to stratified Mackay, oh, sorry, I guess, yeah, I think I wanted this like that, right? And this is now this is Ah, right. Okay, sorry. I was thinking about the guy in the product. Let me just do the trace of this. All right. It's not so hard to see. And this is sort of well known that this is actually equivalent to, and I should have really changed my notation to make this clear. So this is so where y plus y naught over 0 is just the stratified Mackay. So all right, this is like nonlinear causal duality. I mean, it's a result of Umit Isaac, and there's other work by Shipman on this type of equivalence. Okay. So what you get from this is you get a Fourier-Mackay kernel for stratified Mackay. Okay. Built from using this Q construction. Okay. So we had to pass the matrix factorizations, but at least we have one holistic idea here that allows us to construct a Fourier-Mackay kernel. And I should say, having a Fourier-Mackay kernel is not new. This is well known. One of the consequences of very nice work by Kautis, Kamitzer, and Licata. So they constructed Fourier-Mackay kernels for stratified Mackay flops using some categorical SL2 actions. My knowledge of linear causal duality is perhaps not as good as it should be, but the computations that we've done indicate that these are not Kautis's, these are not the CKL kernels. So the CKL kernels are the qualifications of the fiber product itself. These seem to be honest complexes. And so, moral of the story is that, the fiber product itself may not, does not give an equivalence for stratified Mackay, but it turns out that you can use the fiber product, but of a matrix factorization model for it and get out a Fourier-Mackay kernel. All right, so with that, I've gone about a minute over. I'll stop there and thank everyone for their attention.
Any questions for Matt? Okay, let me go offline and then you can ask offline questions. How about that?